Now, we've came to the point where we've said, okay, we know the opposite's going to attract and like charge is going to repel. A fellow by the name of Coulomb started to ask the question, does the distance between the charges matter? Does the amount of charge matter? So kind of what he did was he hung a charged rod, and he'd bring in another rod, measure the deflection. That told him something about the electric force between two charges. And he found out that it's actually going to be proportional to the product of the charges, and it's going to be inversely proportional to the distance that's kind of separating the two charges. And so Coulomb's law was born, which tells us the amount of force in newtons is going to be equal to some constant k. This is just a constant, 9 times 10 to the 9th newtons meters squared per coulomb squared. And here we're going to have just the magnitude of the charge. So this is going to be charge 1. And this is going to be charge 2. Unit of charge is going to be a unit of coulombs. And again, this is just the magnitude, so no signs. We're not going to put negative signs in there. And then the distance of separation squared, so kind of a center to center distance. And this gives us the magnitude of the force, and it's kind of up to us to figure out the direction. If both of these guys are positive, we know that the force is going to be kind of outward like that. If one of these guys is positive and the other guy is negative, then it's going to be kind of an attractive force. And Newton's third law says that this force is going to be equal to that force. So the forces on these two charges are going to be equal and opposite. Just to kind of continue on Coulomb's law, by the way, Coulomb's law is worth definitely a star. The force is going to be along the line connecting the charges. So if I have two charges as in figure A, and I kind of drew a dashed line here connecting the charges, the force is going to be, as you can see, along that line. And once again, we use Coulomb's law right here to figure out the magnitude. So we take absolute values of the charges, figure out the amount of force, and then we say, hey, do we have two positive charges? In that case, the force is going to be repulsive. So I know the direction. Are we talking about two negative charges? Okay, well, that tells me that the direction is going to be outward. And if they are the same charges, that tells me that the force is going to be inwards. So again, use Coulomb's law to figure out the magnitude of the force, and then use what you know about positive and negatives to figure out the direction. And just a little bit more about Coulomb's law. I've already said that the unit of charge is named after Coulomb, who did a lot of work with the forces of charges, and kind of abbreviated with a capital C. Very frequently you'll see stuff like, charge 1 is equal to, let's just say, -5 microcoulombs. It turns out that a coulomb is a huge amount of charge. On the next slide I'll show you the charge of one single electron. So we're talking about, very typically, if we rub stuff together, we're talking about things on the order of microcoulombs or nanocoulombs. So these are going to be slightly different units than you were used to in the mechanical world. So 1 microcoulomb is 10 to the negative 6 coulombs. 1 nanocoulomb is 10 to the negative 9th coulombs. So get kind of familiar with these micros and nanos, because you're going to be seeing them quite a bit. So we could also say that that's going to be -5 times 10 to the negative 6 coulombs. Once again, this constant of proportionality, I rounded it to 9 times 10 to the 9th, but this is going to be a more formal value for it. Typically you can get away with using 9 times 10 to the 9th, and that'll be close enough for government work. And as advertised, just to give you a feeling for the magnitude of the charge on an electron, it's going to be 1.6 times 10 to the negative 19th coulombs, and technically that's going to be a negative. It turns out that this is the same exact charge that's going to be on a proton, so the charge of a proton is also going to be 1.6 times 10 to the negative 19th coulombs. And essentially electric charge is going to be quantized in the units of electron charge. What that quantized means is any charge we're going to see is actually going to be integer multiples of the charge on an electron. We're never going to see a charge be equal to 1/2 the charge of an electron. This can't actually happen. Now you might also see Coulomb's law, which we've already said is k(q)q over r squared, written in terms of this epsilon naught, which is the permeability of free space. So essentially it looks pretty much this value right here is going to be equal to k, which again is equal to about 9 times 10 to the 9th newtons meters squared per Coulomb squared. And this epsilon naught is going to pop up every once in a while. We're going to see it in Gauss's law, so make sure you're kind of familiar with it. Essentially it's just 1 over 4 pi k, and here's the value for it and the units associated with the permeability of free space. Now, Coulomb's law is only going to apply to single point charges, where we're going to say the force is equal to k times charge 1, charge 2, divided by the distance of separation squared. Suppose I have multiple point charges, then I'm just going to use the superposition principle and say I'm going to calculate the force from every charge on every other charge, and then just add them as vectors. So here I have 3 charges, Q1, Q2, and Q3, and we say, hey, what's going to be the net force on Q3? Well, very simply, let's just take a look at charge 1 and charge 3. We know the distance of separation squared, so we know r squared. And I'm going to say, hey, charge 1, charge 3, so now I have force 3, 1, kind of given right there, and we can see it's going to be along the line that's connecting these guys. Similarly, we can do charge 2, charge 3, and calculate force 3, 2, and again this is going to be 3, 2, and this is going to be 3, 1, and we can just straight up calculate these two forces. We know that force Q2 is positive and Q3 is positive, so that force is going to be along the y-axis here. We know that Q1 is negative and Q3 is positive, so it's going to be a force of attraction. So we use what we know about the positive and negatives to figure out the direction of the forces, and we use Coulomb's law to figure out the magnitudes. And then what we can do is we can simply add these guys as vectors, where this guy's along the y-axis, so we would just say force 3, 2 has just a y component, and then we would take force 3, 1 and break it up into an x component and kind of a y component, and essentially add the x's and add the y's, and then we have a resultant force, which your intuition would say it's going to be off in this direction. And we could also calculate the angle knowing the components of the resultant force. So just a little bit of a refresher about net force. If I've got, suppose, an object, some charge, and I've got more than one forces acting on it, so force 1, force 2, force 3, so on and so forth, then the net force is going to be just force 1 plus force 2 plus force 3, force 4, so on and so forth. Keeping in mind that we need to add these guys like vectors, so we need to essentially split it into components and add the x's and y's separately. Now just a very quick review on vector addition. Suppose we had just two simple forces acting on an object. We've got some weird angles going on here. We could do the parallelogram method. We could do the tip to tail method. Most often than not, what you're going to do is we're going to split these two forces into components. So here we've split force 1 into its y and x components. Force 2 we're going to split into the y and x components, kind of knowing what these angles are, so geometry is going to come back to haunt you. And then we're going to say, what is the sum of the forces in the x? Here we can see that it's going to be force 1y minus force 2y, because force 2y is in the negative y direction. Sum of forces, make that in the y direction, sum of forces in the x is going to be force 1x plus force 2x, because both of these guys are in the positive x direction. So make sure you're kind of familiar with some of these 2-to-1 concepts. Now this concept, the next concept is that of electric field. And essentially we can kind of say, hey, suppose I've got just a positive charge as we see in A right here, and I bring in kind of a test charge, and the test charge is always going to be positive. I say, hey, what direction is the force? The force is going to be away, and it's going to be away kind of radially. You can kind of see as I move my positive test charge around this charge, the force is always going to be kind of pointing in this direction right there. The same is going to be true for a negative charge, where I can say, hey, I'm going to have some test charge, and I'm going to kind of move it around this negative charge as seen in B. I'm always going to kind of feel a force kind of pointing inwards, regardless of where I choose to point my test charge. So that kind of gives us the idea that there's kind of some field that's surrounding both positive and negative charges. This field is called the electric field. the key to the electric field is we don't actually need to have that positive test charge to know that there's a field there. That field will always surround positive and negative charges. So what we can do is we can say, hey, all I'm going to do is I'm going to divide out the test charge. Remember that force is equal to charge 1, charge 2, I forgot my K, divided by distance of separation squared. So let me just say, hey, I'm going to take this test charge out, and I'm left with just my electric field being equal to kq divided by distance squared. And I can also say, hey, my electric field is just going to be my force divided by the magnitude of the test charge. So now I can say, suppose I don't know what type of charge I have, but I observe an electric field right there. What happens if I go ahead and I place a positive test charge in this electric field? Well, it's going to feel a force. Kind of rearrange this very important equation right here to say that the force is going to be equal to the charge multiplied by the electric field. And if this charge is going to be positive, then it's going to feel a force in the direction of the electric field. If this charge is going to be negative, then it's going to feel a force in the opposite direction of the electric field, because we'll be putting in a negative charge into an electric field. And the last thing I want to mention about the electric field is going to be the units. Here we can see that force is always going to have a unit of newtons. Charge is always going to have a unit of coulombs. So the electric field units is going to be a newton per coulomb. I'll talk about it in the next lecture. You might also see a volt per meter. So that's going to be the units of electric field, a newton per coulomb. And this slide right here simply gives you the same equations, only in the two different flavors, the one with the epsilon naught and the one with the constant K. And it turns out that I've already talked to this equation, which is just rearranging F is equal to, or electric field is force divided by charge. I can use the same superposition principle for electric fields that I did with the forces. I can say, hey, suppose I've got some distribution of charges, kind of like this. Then I can say, okay, well, this one's going to have an electric field that's always going to point away from it. This one's going to have electric fields that kind of point in that direction right there. And this one's going to have electric fields that always point towards it. So I could pick some point right here and say that the electric field is going to be the electric field from 1 plus the electric field from 2 plus the electric field from 3. Again, adding them as vectors as we did with the forces. Just kind of some notes to think about when it comes to problem solving for electric forces and fields. The very first thing I always do is, if I don't have a diagram, is I draw a picture. Make sure I have the charges with the signs. And then what I can do is, if I know the signs, I can draw the directions of the electric fields. I can draw the directions of the forces. We can use Coulomb's law to calculate the magnitude, use our knowledge of positives and negatives to figure out the directions, and then we add the forces vectorially to get the final end of the day result. And I'm coming back to this slide once again. These electric field lines are always going to start on the positive and move away from it, and they're always going to kind of end up on a negative going towards it. Now when we're taking a look at electric field lines in the pictures, it turns out that the number of electric field lines is going to depend on how much charge. So here, suppose that this guy just represents a charge of Q. If I had a charge that was maybe 10 times that charge, 10Q, then what I would do is I would say, hey, there's going to be a whole heck of a lot more electric field lines pointing away from this positive charge. Kind of conceptually, you can see that the electric field is going to be stronger when the lines get closer together. We know that the electric field is going to go like 1 divided by r squared. So as these lines of electric field get more and more and more separated, the electric field is going to get weaker and weaker and weaker. As the lines get closer and closer together, then the electric field is going to get stronger and stronger and stronger. Now, you may be asking yourself, well, what would the electric field lines look like if I had an electric dipole, which, if you remember from the beginning of the chapter, was two charges that are opposite in sign? We know that the electric field lines are always going to point away from the positive and point towards the negative. And it turns out that we're going to get some weird, funky looking patterns with this electric dipole. Still, we're always going to have electric field lines pointing away from positive and towards the negative. If I ask myself what is the electric field at any given point, it's actually going to be tangent to these electric field lines at any given point. So if I were to draw it here, it would kind of be in that direction. If I were to draw it here, it's going to be in that direction. Up until this point, all my electric field lines have been straight. Now I have some electric field lines that have some curve to them. Now, what would happen if I had two plates and I had some charge distribution of equal magnitude and opposite direction on those two plates? Well, what we can kind of do is we'll say the charge is going to be uniformly distributed throughout the two plates. Let me just kind of pick some point in the middle right here. Say, what is the electric field at that point right here? Well, there's going to be an electric field, kind of on this point from these two charges. And in your mind's eye, you can see that it will kind of cancel itself out. In the y direction, there will only be some electric field in the x direction. Similarly, we got this one. It's going to kind of add up in that direction. You could argue the same thing for these two negative charges, and because of the symmetry of the problem, we could do it for those positive charges and these positive charges. The end result is going to be that the electric field lines are going to go from the positive to the negative, and for the most part be straight lines from the positive charge to the negative charge. Now, the magnitude of the electric field inside of this, inside of these evenly spaced parallel plates is actually going to be a constant. So the electric field is going to be a constant. And this is actually going to be a fairly important slide when we come back and talk about capacitors. And let's just kind of finish off electric field discussion. Field lines are going to indicate the direction of the electric field. The electric field is actually going to be tangent to the line. The magnitude of the field is going to be proportional to the density of the lines. And probably the most important is the field lines are going to start on positive charges and end on negative charges, with the number being proportional to how much charge we actually have there.